Hey everybody, welcome to chapter 11 on multiple regression. So we're moving beyond just the simple linear regression we talked about in chapter 10 to now talking about multiple different predictor variables, all predicting one outcome variable. So again, in multiple regression, we've got more than one predictor variable and we're trying to predict a single outcome variable. So we've got more than one x variables or independent variables and one y variable, outcome variable, dependent variable, all those meaning the same thing. But still, all of these variables have to be numeric. They have to be numbers. There's no categorical data, no nominal or whatever data involved in multiple regression. In research, we use multiple regression all the time. And the reason is because typically when you think about trying to predict some kind of outcome, there are a lot of possible factors that could influence that outcome. So for instance, using a non-psychology examples, you could predict the price of a used car. Well, what would you want to know? What kind of information would you want to know about that car that would probably influence how expensive it is? Well, you'd want to know how old it is. Very, very old models oftentimes cost less unless they're like collector's editions. The mileage, the more miles that's on the car, the less it's worth. Its condition, is it damaged in any way? Does it still run? And all those kinds of things. All of those factors combined will help you predict what the price of a used car should be. Same thing for risk of heart attack, right? Well, it really matters what age the person is, what their current blood pressure is, what their diet and exercise habits are like. Have they had a heart attack in the past? What are their medications? Like, there's all kinds of factors that influence outcomes of interest. And so we would want to figure out some kind of statistical analysis that takes into account all those factors. And here, multiple regression really, really, really does a great job. All right, a couple of review questions. I want to know if people who sleep less tend to drink more coffee. For this, I would run what kind of analysis? This would just be a bivariate correlation, a correlation. We've got two variables, sleep and drinking coffee, and we want to know in general what's the relationship there. All right, what if I wanted to predict exactly how much coffee someone would drink if they slept 5 hours last night? What would be the best analysis to use in this case? Here you're trying to make a prediction. You're actually trying to predict the value of the outcome variable based on the value of the predictor variable. And so therefore, you're going to want to use linear regression. And finally, I want to know if coffee consumption and amount of homework predict how much sleep someone gets. In this case, I would use, for this one, you're going to use multiple regression because you've got two x variables, two predictor variables, coffee and homework, and you're trying to use both of those to predict how much sleep someone would get. In that case, you've got two variables predicting one outcome variable. That is multiple regression. So let's use a psychology example to start talking about kind of the theoretical underpinnings of multiple regression. So with simple linear regression and with correlation, you just have two variables, right? You just have one variable that in the case of linear regression is predicting the other variable, or in correlations, you're just seeing how do those two variables tend to go together? What is their relationship like? The example here is of extroversion and happiness. So we've got kind of a Venn diagram here looking at the left circle, it would be extroversion, the right circle would be happiness. And for both simple linear regression and with correlation that just has two variables here, basically what we'd be interested in finding is this part of the diagram right here that I've highlighted. We were interested in the overlap, the actual relationship between extroversion and happiness. Now let's say I'm interested in a second predictor variable. So now we have extroversion and loneliness, and we're going to be trying to see what the relationship between extroversion and loneliness are with happiness, right? Well, this is kind of interesting because almost certainly extroversion has an effect on happiness, loneliness has an effect on happiness, but also there's going to be a relationship between extroversion and loneliness. And that would be represented by this part. So extroversion is related to loneliness, but also we're going to see here in just a second that extroversion and loneliness might have some overlap in the part of happiness that they explain. So for instance, they might both explain a little bit of the same part of happiness, and that is going to be represented by this area here. So that very, very middle piece that kind of connects all three of the variables, that might be where extroversion and loneliness actually are explaining basically the same part of happiness. Okay, and that's a little bit of a problem because usually when we do regression analyses and in multiple regression, we want to know, well, I want to know the sort of pure effect of extroversion on happiness or the pure effect of loneliness on happiness, regardless of or independent of the other predictor variables. So I want to know, how does extroversion predict happiness independently of loneliness? Or I want to know, how does loneliness affect happiness independently of extroversion? Okay. So for loneliness, if I was just interested in the effect of loneliness on happiness, how are loneliness and happiness related? I want to know that independently of extroversion, of the effect of extroversion. So I'd really only be wanting to look at kind of this part of the Venn diagram, right? Not with that overlap between all three of the variables, but just this piece right here where loneliness is related to happiness. So in order to talk about multiple regression a little bit more in detail, and especially when we want to be interpreting output from a multiple regression analysis, we've got to talk about a few terms, a few new kind of nomenclature and terms here. So here we're going to be looking at something called capital R, not lowercase r. Lowercase r is for a bivariate correlation, right? A Pearson's correlation. Now we're going to be using what's called capital R, which is basically a multiple correlation coefficient. It says what's the effect of all of the predictor variables on the outcome variable. You couldn't do that with a regular correlation. So in multiple regression, there's something called capital R, or just R, and that basically is a correlation coefficient that tells you how are all of the predictors combined related to the outcome variable. R squared we talked about when we talked about linear regression analyses. R squared is the amount of variance in the outcome variable that is explained by all of the predictors. And it's literally, you just take capital R and you square it. And that is the amount of variance in the outcome variable that is explained by all the predictors. Now we're going to have a couple of different things. B is going to be the slope, and it's called an unstandardized coefficient. Okay, it's an unstandardized regression coefficient, B, and that is the slope of each individual predictor variable. So you'll have multiple values of B, one for each of the predictor variables that you have, and the interpretation of B is how much does our outcome variable increase or decrease for each 1 unit increase in X. So for instance, how much happiness does somebody increase or decrease for every 1 unit increase in either extroversion or 1 unit increase in loneliness? Now beta is a standardized regression coefficient or regression weight, and that is basically how many standard deviations the y variable increases or decreases for each 1 standard deviation increase in the x variable. So that's kind of like a slope, but it's standardized. With beta, the cool thing about beta is that because it's standardized, basically what you can do is look at whichever variable has the most extreme beta, meaning like the most positive or the most negative value, And that tells you which of the predictor variables actually is having the largest overall effect on the outcome variable, whether it's positive or negative. So if we find that loneliness actually has a larger absolute value of beta than extroversion when we're talking about its effect on the outcome variable, that means that loneliness is kind of more important, or it's a better predictor of happiness than extroversion. So that's kind of interesting. The other thing that I wanted to mention is beta and B, the slope of the predictor variables, both of those things are the slope or the standardized correlation, standardized regression coefficient of one X variable independently of the other variable, or you might even say controlling for the other variable. So the nice thing about this is that when we see the effects, meaning the slopes and the betas of each individual X variable, each predictor variable, those numbers have already basically subtracted out the effect of the other variable. So you're only seeing kind of the pure effect of each variable at a time. And that's pretty awesome. So let's walk through a little bit of a statistical example going through the relationship between extroversion and happiness, loneliness and happiness, and then the combined relationship of extroversion and loneliness on happiness. So here what we have are just simple bivariate correlations. This is just the Pearson's R, right? And so what you see is extroversion is correlated with happiness at R equals 0.65. And you can tell that that's a significant relationship because the p-value is less than 0.05. Okay. So what that tells you is extroversion is positively related to happiness, which makes sense. People who are extroverted tend to be happier. And it's a fairly strong correlation. 0.65 is a fairly strong correlation. Okay. Loneliness is related to happiness at an R of negative 0.52. It's also significant because you can see that the p-value is going to be less than 0.05. The R of negative 0.52 tells you that this is a negative relationship, right? So the more lonely someone is, the lower their happiness. Or conversely, the more happy someone is, probably the lower their loneliness. Okay? You don't know exactly in what direction these things affect each other because this is correlational data. So these are some nice little correlations, but what we're interested in is having extroversion and loneliness predict someone's happiness. And I want to see, how does extroversion affect happiness controlling for loneliness or independent of loneliness? And also, how does loneliness affect happiness controlling for or independently of extroversion, sort of taking out the relationship between extroversion and loneliness on happiness? So let's see what that would look like. Okay, so let's say we actually conducted a multiple regression analysis, and now we get some output that looks like this. The R value, which is again the multiple correlation coefficient, is going to be 0.70. That is the combined effect of extroversion and loneliness related to happiness. That's the combined relationship. Okay. And that's also p is less than 0.05, so that's going to be significant. By the way, the output of the analysis that you conduct in R or whatever statistical software program you use, it'll tell you what the p-value actually is. It'll say, p equals 0.003 or something like that. Anytime in this class that the p-value is less than 0.05, because remember, that's actually our alpha. Our alpha is 0.05 in this class. That's our decision criterion. Anytime that a p-value is less than that, that means it's highly unlikely, and it means that you get to reject the null hypothesis. So a p-value of less than 0.05, less than our criterion, is a significant result. Okay, so let's just say it was less than 0.05. So this is a significant multiple correlation coefficient of extroversion and loneliness with happiness. But then we get to see the individual effects of extroversion and loneliness on happiness. So for instance, we might find that the slope of extroversion, which would be an unstandardized correlation, or rather regression coefficient. Let's say that that's 0.11. 0.11. And that means that with every 1 unit increase in extroversion, somebody's happiness increases by 0.11 units of happiness. But wait, this is interesting. The p-value is above 0.05. Again, this would all be on the output, so you could actually see what it is. The p-value is above 0.05. That means that's not a significant effect. But that's weird because we found earlier that the correlation between extroversion and happiness was significant. R equals 0.65. The p-value was less than 0.05. So what's going on here? Well, let's take a look at the loneliness effect on happiness first. So loneliness, the slope is negative 0.70. That means that for every 1 unit increase in loneliness, happiness decreases, or we would predict happiness to decrease by 0.70. And that is a significant effect, a significant slope. P is less than 0.05. So what's happening here is that if you have extroversion trying to predict happiness, but you're controlling for loneliness, extroversion on its own actually isn't a significant predictor of happiness, because it was actually loneliness and extroversion together. It was sort of like the part of extroversion that is actually related to loneliness that was having an effect on happiness. But in multiple regression, each of these variables controls for the other variable, or each of them it's showing its independent, pure relationship to happiness. So extroversion actually kind of drops out. It's not actually that important anymore. And instead, loneliness actually explains or can predict happiness when it's controlling for extroversion. All right, so these are important concepts, so I want to go over another example. And this one is an example you are familiar with. So we've talked about in class how ice cream sales and homicides are related. And you can see that in a correlation. So here we have ice cream sales and homicides are related at a correlation coefficient of 0.35. So more ice cream sales is associated with more homicides. But of course, we're missing a hidden third variable, right? Which is temperature, heat, which causes aggression, and then that indirectly causes more homicides. So let's try to find out how all three of these variables act together. So we have a correlation coefficient for temperature and homicides of 0.40, indicating that higher temperatures are related with higher homicide rates. But again, these things are just correlations. These are just natural relationships between variables, and they're not controlling for anything. So we can use multiple regression, and that might show that the combined multiple correlation coefficient of ice cream sales and temperature on homicide is R equals 0.44, which is significant at a p-value of less than 0.05. But then if we look at the effect of each of our predictor variables independently on homicide, so ice cream sales predicting homicide, the slope is only 0.01, and that is a non-significant slope because we can see the p-value is above 0.05. Meanwhile, our temperature predicting homicide, the slope is 35.23, and that is a significant slope. And the direct interpretation of the slope would be that for every 1 degree increase in temperature, we would expect or predict 35.23 more homicides. So you can see again, it's not the ice cream sales themselves that have any predictive value of homicides. It's the temperature. And so temperature is going to remain a significant predictor when you put it all into this multiple regression model. But ice cream sales drops out because ice cream sales before was related to homicides only when you didn't also control for temperature. Now, in the previous two examples that we've just gone over, I've showed you that even though the correlations for the predictor and outcome variables are significant, then when you do a multiple regression, one of those predictors basically drops out. It becomes non-significant when controlling for the other predictor. But that's not always the case. Like however many predictor variables you have in the model could all be significant, or one of them could not be significant, or multiple of them could not be significant when you enter all of them into a multiple regression. So for instance, like if you think about happiness as an outcome, well, what kinds of things probably predict happiness? I would guess your health. Your health status probably predicts your happiness to some degree. And the quality of your close relationships probably predicts happiness to some degree, right? Both of those, if you tried to predict happiness on both of those variables at the same time, it's totally possible that both of them remain significant predictors of happiness and that you would find both of their slopes to have a significant p-value of less than 0.05. Totally possible. So it's not like the examples that I've given here today are always the case. Okay, everybody. Hope you enjoy this meme. We're going to go over some more in-depth examples of multiple regression in the next video.